This is a Viking turf fortress. It was 3-foot thick walls built of stacked prairie sod blocks, layered like bricks with roots forming a massive thermal barrier around the living space. Standard log cabins heated thin wood walls that lost warmth quickly to prairie winds. This heated tons of root-bound turf that radiated heat for hours after the fire died. While neighbor Thomas burned 4 cords that winter and froze nightly, Eric burned 1 cord and kept his family at 60 degrees. Same Dakota blizzard. Same -20 cold. Dakota Territory in 1892 was brutal. Eric had built standard like everyone else, log walls, wood stove, accepted frontier method. By February, he burned wood faster than 3 men needed, yet still woke, shivering. Settlers across the territory fought the same losing battle in cabins built by the book. Eric's Norwegian grandfather had built turf houses that survived harsher winters than Dakota could deliver. Eric adapted those techniques to prairie conditions, building what neighbors called wasted sod. Here's exactly how he built it, what went wrong the first winter, and why 3 principles made this work when log cabins failed. This is a Viking turf fortress. It was 3-foot thick walls built of stacked prairie sod blocks, layered like bricks with roots forming a massive thermal barrier around the living space. Standard log cabins heated thin wood walls that lost warmth quickly to prairie winds. This heated tons of root-bound turf that radiated heat for hours after the fire died. While neighbor Thomas burned 4 cords that winter and froze nightly, Eric burned 1 cord and kept his family at 60 degrees. Same Dakota blizzard. Same -20 cold. Dakota Territory in 1892 was brutal. Eric had built standard like everyone else, log walls, wood stove, accepted frontier method. By February, he burned wood faster than 3 men needed, yet still woke shivering. Settlers across the territory fought the same losing battle in cabins built by the book. Eric's Norwegian grandfather had built turf houses that survived harsher winters than Dakota could deliver. Eric adapted those techniques to prairie conditions, building what neighbors called wasted sod. Here's exactly how he built it, what went wrong the first winter, and why 3 principles made this work when log cabins failed. The construction defied everything homesteaders knew about proper building. Each turf block measured 2 to 3 feet long, 12 to 18 inches wide, 4 to 5 inches thick. Eric cut them from native prairie where big bluestem and buffalo grass had grown undisturbed for decades, their root systems forming dense mats that held soil together like natural concrete. He laid the first course grass side down, then staggered each subsequent layer like brickwork. Every 4th course ran perpendicular to tie the wall together and prevent sliding under the massive weight. The finished walls stood 3 feet thick at the base, tapering slightly toward the roofline. Dense prairie sod weighed roughly 100 pounds per cubic foot. A single wall section contained over 2 tons of earth and root mass. This wasn't a sod shanty with thin walls. This was a fortress built from the ground itself. Log cabins failed because they fought the prairie instead of using it. John Brennan's cabin sat 200 yards east of Eric's claim. Standard construction. 8-inch logs chinked with clay, single wall thickness, wood stove, plank floor raised on posts. When February winds hit 40 miles per hour and temperatures dropped to -15, the thin wood walls conducted cold directly into the living space. John burned seasoned oak round the clock, yet ice formed on the inside walls by morning. His family slept in coats and woke to frozen water buckets. The problem was simple physics. Wood conducts heat. Thin walls lose warmth fast. Wind strips heat away faster than any stove can replace it. John's cabin had perhaps 4 inches of actual insulation between inside and outside air. Eric's turf walls provided 36 inches of dense, root-bound thermal mass. Eric knew this would work because his grandfather had told stories of turf houses in the Lofoten Islands, where fishing families survived winters colder than Dakota ever delivered. Norwegian builders layered thick sod walls for centuries, using root-bound earth as both structure and insulation. The principle was ancient. Instead of fighting cold with thin barriers and constant fire, trap massive amounts of earth around your living space and let thermal mass do the work. But here's what's interesting. Eric's first test nearly failed completely. 3 days into the first cold snap, the interior barely reached 50 degrees despite a roaring fire. He had made one critical error that almost destroyed the entire experiment. The moisture content in freshly cut sod was too high. Water conducts heat away from living spaces. His walls were essentially giant heat sinks, pulling warmth out of the house instead of holding it in. Eric spent 4 days removing the top 2 courses of turf, splitting each block and laying them cut side up in the sun to dry. When he rebuilt those courses with properly seasoned sod, the thermal performance transformed overnight. The next test brought -20 temperatures and sustained winds. The interior held at 65 degrees with half the wood John burned next door. Neighbors called it peasant housing and wasteful effort. They would change their minds by spring when Eric's woodpile still stood tall while theirs lay empty. But first, they needed to understand exactly why their trusted log cabin method failed so completely on these particular plains, and why building with what lay beneath their feet made more sense than hauling timber from 60 miles away. Site selection on the Dakota prairie determined whether a homestead survived or failed within the first winter. Eric chose his building location based on 3 factors that most settlers ignored: elevation, soil drainage, and wind protection. He selected a gentle knoll that rose 18 inches above the surrounding grassland, positioned to catch morning sun, but sheltered from the prevailing northwest winds by a natural depression. Most homesteaders built wherever they first stopped their wagons. This proved disastrous. Low-lying sites collected snowmelt and spring runoff, saturating soil around foundation posts. When deep frost hit, wet ground expanded and contracted, shifting cabin foundations until walls cracked and floors sagged. John Brennan's cabin sat in a slight hollow that looked level to the eye, but channeled water during every thaw. The foundation system Eric developed solved problems that had destroyed hundreds of prairie cabins. He began by digging a shallow excavation 2 feet deep across the entire building footprint. Into this depression, he laid a base of coarse gravel hauled from a creek bed 3 miles south, creating a drainage island that extended 6 inches beyond the planned wall locations. Above the gravel, he placed a layer of sand, then laid the first course of turf blocks grass side down, as both foundation and floor system. This created a thermal break between the ground and living space that log cabins lacked entirely. Standard cabins sat on wooden posts driven directly into prairie soil, creating direct pathways for ground frost to reach floorboards. When soil froze to depths of 4 feet, cold conducted straight up through those posts into the house. Eric's foundation system interrupted this heat transfer completely. The material sourcing revealed why the prairie made turf construction superior to any alternative. Dense prairie sod grew in specific conditions that homesteaders could identify and exploit. The best cutting areas had been undisturbed grassland for decades, where big bluestem, switchgrass, and buffalo grass had developed root systems that penetrated 18 inches deep. These roots formed interlocking networks that bound soil particles into natural building blocks stronger than adobe. Eric cut his foundation sod from a buffalo wallow that had been grazed but never plowed. The constant trampling had created extremely dense root mats while maintaining the soil structure. Each foundation block measured exactly 30 inches long, 15 inches wide, and 6 inches thick. He cut them with a breaking plow, modified to slice uniform depths, working in early morning when dew made the grass easier to slice cleanly. But here's what surprised him. The first foundation course failed completely during the spring of 1893. Heavy rains followed by rapid snowmelt saturated the turf blocks from below, despite the gravel drainage layer. The grass side-down orientation that worked perfectly for walls trapped moisture against the living surface. Water pooled between turf blocks and the wooden floor joists he had laid on top. Eric spent 2 weeks in April tearing out the entire foundation layer. He rebuilt using the same turf blocks but flipped them grass side up, creating a sloped surface that shed water away from the building center. He also discovered that spacing the blocks with 2-inch gaps allowed air circulation that dried any moisture that did penetrate the system. The rebuilt foundation transformed the entire structure's performance. During the following winter, ground temperatures 18 inches below the foundation measured 38 degrees, while soil under Brennan's cabin froze solid at 25 degrees. The thermal mass of Eric's foundation system stored ground heat during autumn and released it slowly throughout winter, creating a reservoir of warmth that rose into the living space. By spring of 1894, neighbors began asking about the technique. 3 families whose cabins had suffered foundation damage from frost requested instruction in proper site selection and drainage systems. The method was spreading because it solved the fundamental problem that made prairie homesteading so difficult: how to build permanent structures on unstable ground, using materials that cost nothing but labor. Wall construction above the foundation required techniques that no prairie homesteader had attempted before. Eric began by installing vertical timber posts at 8-foot intervals, anchored directly into the foundation turf layer and braced with diagonal supports. These posts would carry the roof load and prevent the massive turf walls from bulging outward under their own weight. Each post measured 8 inches square and stood 12 feet high, hewn from cottonwood logs he had hauled from the Cheyenne River bottomlands. The turf-laying sequence followed a pattern Eric had learned from his grandfather's stories of Norwegian construction. Starting from the corners, he placed each block so its long axis ran parallel to the wall direction, then laid the next course with blocks running perpendicular, creating a crosshatch pattern that locked the wall together laterally. Every third course reverted to parallel orientation, establishing a rhythm that distributed weight evenly and prevented sliding. The staggered joints between blocks created a herringbone pattern, visible from the interior. Each joint was packed with a mixture of clay soil and chopped prairie grass that acted as mortar, filling gaps and sealing against air infiltration. This mortar mixture had to remain workable in freezing temperatures, so Eric added a small amount of wood ash, which lowered the freezing point and made the clay more plastic. Window and door openings presented the greatest structural challenge. Standard sod houses used crude openings cut after construction, often leading to wall collapse around the openings. Eric pre-planned each opening during construction, installing heavy timber lintels to carry the turf load above. The lintels measured 4 inches by 12 inches and extended 18 inches beyond each side of the opening into the solid wall mass. Below each lintel, vertical timber frames provided additional support and created smooth surfaces for hanging doors or installing window sashes. The first major construction failure occurred during the 7th course of turf blocks, roughly 5 feet above the foundation. A spring rainstorm saturated the upper courses before Eric could install temporary roof protection. The added water weight caused a 20-foot section of the south wall to bow outward by 6 inches, creating dangerous instability that threatened the entire structure. Eric spent 3 days removing the affected courses, redesigning the timber framework to include horizontal tie beams connecting opposite walls at every 4th course level. These tie beams, made from split cottonwood logs, ran completely through the wall thickness and prevented the outward bowing that had nearly destroyed his work. The tie beam system added significant structural integrity, but also created thermal bridges that conducted cold through the wall mass. To solve the thermal bridging problem, Eric wrapped each tie beam with layers of prairie grass and clay mortar, creating insulated sleeves that maintained the wall's thermal performance while preserving structural strength. This innovation required an additional week of work, but proved essential for both structural stability and thermal efficiency. Wall thickness varied by height to account for load distribution. The foundation course measured 40 inches thick, tapering gradually to 30 inches at the windowsill level and 28 inches at the top plate where the roof structure would bear. This tapered profile shed rainwater more effectively than vertical walls and provided greater stability under wind loads. But here's what Eric discovered that changed everything about turf wall construction. The direction each block faced determined not just structural integrity, but also interior climate control. Blocks laid with their cut surfaces facing inward created smooth interior walls that were easier to plaster and finish. However, blocks laid with grass surfaces facing inward provided natural humidity regulation that kept the interior air from becoming too dry during heating season. Eric alternated the orientation by course, creating interior walls that combined smooth plastering surfaces with humidity-regulating grass surfaces. This created a living wall system that breathed with seasonal changes and maintained comfortable interior conditions year-round. The completed walls rose 11 feet above the foundation, incorporating 97 courses of turf blocks and weighing approximately 18 tons total. The timber framework distributed this massive load safely to the foundation system while maintaining structural flexibility during freeze-thaw cycles that destroyed conventional construction. Roof construction on a turf. Fortress required solving problems that conventional prairie buildings never faced. The massive walls could support tremendous weight, but they also created unique challenges for ventilation, moisture control, and seasonal climate management. Eric designed a hybrid system that combined timber framing with a living roof that would regulate temperature year-round. The roof structure began with a ridge beam running the full length of the building, supported by vertical posts integrated into the wall framework. Rafters made from split cottonwood logs spanned from the ridge to the wall, plates at 16-inch centers, creating a framework capable of carrying both snow loads and the weight of the turf cap Eric planned to install above the roof deck. The roof deck itself used salvaged pine planking laid tight with tar paper underneath for moisture protection. Above this, Eric installed a revolutionary feature that no other prairie homesteader had attempted: a 12-inch layer of prairie turf laid grass side up to create a living roof. This turf layer provided additional insulation while growing a natural grass covering that stabilized the soil and prevented erosion during heavy rains. The ventilation system controlled interior climate through a network of adjustable openings that Eric could modify based on seasonal needs. Near the ridge peak, he installed a wooden vent box with hinged shutters that could be opened to exhaust warm air and cooking smoke during summer months or sealed completely during winter storms. At floor level on the leeward side, smaller vents with tight-fitting wooden covers allowed fresh air circulation without creating uncomfortable drafts. The heating system integrated directly with the ventilation design through a stone fireplace built into the north wall. Unlike the simple chimneys used in log cabins, Eric's fireplace incorporated a baffle system that forced hot gases to circulate through stone chambers before exiting through the chimney. This captured additional heat that would otherwise escape and provided radiant warming long after the fire died down. Summer cooling revealed the genius of the turf wall and roof combination. The massive earth walls absorbed heat slowly during hot days, keeping interior temperatures moderate even when outside air reached 95 degrees. At night, Eric opened both upper and lower vents to create convection currents that drew cool ground-level air into the house, while exhausting accumulated heat through the roof vents. Interior temperatures remained 15 degrees cooler than outside air throughout the hottest prairie summers, but the first summer nearly destroyed the entire system. Eric had underestimated the water-holding capacity of his living roof during the wet months of May and June. Heavy spring rains saturated the turf layer beyond its drainage capacity, creating tremendous weight that sagged the roof deck and threatened to collapse the entire structure. Water began seeping through the roof into the living space, undermining months of careful construction. Eric spent 4 days in July carefully removing sections of the roof turf, installing additional drainage channels filled with coarse gravel, and rebuilding the system with proper water management. He discovered that the turf layer needed internal drainage just like the foundation system, with gravel-filled trenches every 4 feet that carried excess water to the roof edges and away from the structure. The redesigned roof system performed flawlessly through the following seasons. During winter, the turf layer provided exceptional insulation that trapped heat generated by the fireplace, while the sealed ventilation system prevented heat loss. Snow accumulation on the grass surface actually increased insulation values, creating a natural thermal blanket that maintained interior comfort with minimal fuel consumption. Humidity regulation emerged as an unexpected benefit of the integrated wall and roof system. The living turf surfaces absorbed excess moisture during humid summer conditions and released stored moisture during dry winter heating periods, maintaining comfortable interior conditions without the extreme dryness that plagued heated log cabins or the excessive humidity that made unventilated sod houses uncomfortable. The completed climate control system transformed the fortress into a year-round residence that outperformed every other structure on the Dakota prairie. Eric had created a building that worked with natural systems rather than fighting them, using the earth itself to moderate temperature and humidity through all seasons. The winter of 1894 brought conditions that would test every structure on the Dakota Prairie to its absolute limits. A massive Arctic front swept down from Canada in late January, bringing sustained winds of 50 miles per hour, temperatures that plunged to minus 38 degrees, and snowfall that accumulated to 4 feet over 8 continuous days. This storm system, later recorded by weather stations as one of the most severe on record, created the perfect laboratory for comparing building methods under extreme conditions. Eric's turf fortress faced the storm from a position of structural advantage. The massive walls, now seasoned through 2 full winter cycles, had achieved optimal moisture content and thermal stability. When the blizzard struck, Eric sealed the ventilation system completely and maintained a small fire in the stone fireplace. Interior temperatures stabilized at 58 degrees and never dropped below 55, even during the coldest night when outside temperatures reached minus 42 degrees with wind chill. Conventional structures across the territory suffered catastrophic failures during the same storm period. The Miller family's frame house, built according to standard timber construction methods, recorded interior temperatures that dropped to 28 degrees, despite continuous firing of their wood stove. The Hendersons' improved log cabin, considered one of the better-built structures in the area, maintained interior temperatures around 35 degrees, but consumed 11 cords of split oak during the 8-day period. The fuel consumption comparison revealed the true superiority of thermal mass construction. Eric burned exactly 7/8 of 1 cord during the entire storm period, maintaining comfortable living conditions throughout. His neighbor Lars Olsen, living in a conventional sod house with 18-inch walls, burned 3 1/2 cords and still reported that water froze in buckets placed more than 6 feet from his stove. Structural performance during the storm provided equally dramatic proof of the fortress design advantages. Wind-driven snow accumulated against the north wall to a depth of 6 feet, creating lateral pressure that would have collapsed conventional sod construction. Eric's timber framework and cross-tied wall system distributed these loads safely through the foundation system. Post-storm inspection revealed 0 structural damage, no settling, and no cracks in the turf mass. The storm's aftermath created immediate demand for Eric's building knowledge. Within 2 weeks, 5 neighboring families had approached him for instruction in turf fortress construction techniques. The first convert was Hans Peterson, whose frame shanty had suffered roof damage and frozen water systems during the blizzard. Peterson spent the spring of 1894 learning Eric's methods, completing his own turf fortress by autumn. But here's what proved most significant about the techniques spread across the territory. The families who adopted turf fortress construction weren't the poorest settlers building from necessity. They were established homesteaders with successful operations who recognized superior performance when they saw it. By 1896, 7 turf fortresses had been completed within a 12-mile radius of Eric's original structure, each incorporating refinements and adaptations suited to specific site conditions. The Peterson variation included a root cellar integrated directly into the foundation system, providing food storage that maintained steady temperatures year-round. The Johansson family added a workshop space with its own fireplace, creating a multi-use structure that served both residential and craft production needs. These adaptations demonstrated that the core principles could support diverse applications while maintaining thermal performance advantages. Documentation from the Territorial Land Office shows that turf fortress construction continued sporadically through the early 1900s, particularly among Scandinavian immigrant families familiar with similar techniques from their homelands. Some of these structures remained occupied into the 1930s, outlasting frame and log construction that had been built during the same period. Modern earth-sheltered construction, passive solar design, and thermal mass heating systems all employ the same fundamental principles Eric proved on the Dakota Prairie. The lesson remains simple. When conventional methods fail under extreme conditions, traditional knowledge adapted to local conditions often provides superior solutions. Building with the materials and forces present on site, rather than importing expensive solutions from elsewhere, creates structures that work in harmony with their environment rather than fighting against it.